Hi, folks. So in this video, I'm going to talk about transition systems. I just want to note that for the slides, I am using the CSE 505 slides used in the University of Washington 2023 offering of this course by James Wilcox and Zachary Tatlock. Let's start by considering this small program here, which we can also think of as an operating system, a simple operating system that really doesn't do anything but just count infinitely. Notice this is pseudocode. This is not really valid code. And this, for example, is mostly intended to drive the idea of the evolution of a state of a program using small steps, as opposed to working backwards from a goal. So consider the state space of this program. This program only has one variable, and in each step, it just increments that variable. So we only have to keep track of this variable. Now, we know this not to be true that this program can go on forever, because that's not what computers today do. But if we considered the values that x can take on as the space of all positive integers, that space is infinite. X can virtually go on forever if we were to execute this program, because there are no ways to stop this program. So if you think of the states of this program as being reflected on this graph, this program starts by taking on this value 5, and then just keeps on executing. So generally speaking, a transition system has 3 parts. It has to define the states of the system. It should have some initial states, which are a subset of all the states possible. And there should be a transition system which gives you a path from one state of the system to all the possible states from that given state. So let's think of these values. Here we can consider the set of initial states to be natural numbers. We know that our only initial state is 5, so we can just have a set with number 5 in it as our only initial state. And in this case and most other cases, it might be easier to describe the transition system pictorially, but for the sake of just writing it down, we are going to give a definition. And we can say that for all x and y, the state of the program is as such. However, y is our next number, and these are natural numbers. Notice our transition system doesn't put a bound on our initial state. In this case, 4 to 5 could be an edge in our program or in our transition system, given the constraints we have down here. Now notice, if we were to also put the constraint that x is equal to 5 here, we'll have a more strict rule about this transition system. But we're going to consider what are the consequences of including or not including this additional constraint. So let's see how we make steps in our path and transition in this system. So here, this arrow without the star, unlike the example below, says that there is exactly one edge between S1 and S2, or S1 steps to S2, in one step, that is. So exactly one step. This other notation, the arrow with the star, says that there could be any number of edges between S1 and S2. There might be 0, there might be many. But it means that there is a path in S1 steps stars to S2. So it might be 0 steps. It might be another number of steps. And we say that step S is reachable if there is an initial state S0 where we can reach state S from S0 with 0 or more. So going back to our example, here are some valid steps. So we can go exactly in one step from 5 to 6, from 100 to 101, and so on and so forth for the rest of the examples here. But notice, none of these examples at the bottom are valid. We cannot go backwards. We cannot jump twice or go 2 steps at once. And with this particular arrow notation without the star, we cannot step to the same state. Now notice in the star notation, we can go 2 steps forward. We can stay where we were in the same state. We still cannot go backwards in this program. Now notice any state, including 5 and numbers larger than 5, are considered reachable. And any integer or any state smaller than 5 is considered unreachable because we cannot transition into it starting from our initial state 5. Now we can infer from previous slides that 2 is not reachable, just not a reachable program state. And thinking about this is important because invariants like these are how we encode into verifiers the unreachable states of a program. Now, we are going to insert this assert statement as the first line inside the loop in our program. And really what this assert statement is asking us to prove here is to show that this variable x is never smaller than its initial state. In other words, there are no reachable states where this variable is smaller than its initial value, which is. So to show that this is always true, we need to show there are no reachable states where this is false, which changes our proof. And let me just mention that an invariant is a property which always holds in all the reachable states. So we want to show that there's an invariant here. It doesn't vary. The fact that x is greater or equal to 5 does not vary throughout our program. So thinking about invariants might be at first a little bit counterintuitive. Let's look at our graph here. What is always true about our initial state? We cannot say that in our initial state, we know that x is always going to be greater than 6, but we can say that x in our initial state is always greater than 4. We can also say that x is a natural number. So looking at these examples, we see our initial state being equal to or greater than 5 is a correct invariant. It is also correct that our initial state is greater or equal to 4. That always holds. It also is true that our program state is always representing a natural number, and that this program state is never equal to 4. But it's not true that it's sometimes not equal to 6. Obviously it is, if we ever step more than once. Now, let's consider a world where somehow 6 was not a possible reachable state, or we thought to propose it as a possible unreachable state. Obviously, 6 is reachable in our transition system, but we are now claiming that n cannot be 6. But then we cannot say 6 is not equal to 6. That is false. There's a technical term for this. We call it counterexamples to safety. That is, if we have a property P, in this case, our property is that x is equal or greater to 5, but we have a reachable state. In this case, we are proposing that this is our property, that x is never equal to 6. But then we have a reachable state, obviously, that we can step into. But it does not satisfy P anymore. This is a counterexample to safety, and it's a dangerous place to be in because it's reachable and it violates the property that we defined for our state. Another way of thinking of this is if we were to now draw the possible states that our program is allowed to be in, we get all the numbers except 6, and we're starting from 5, but then our transition system allows us to step into 6. So 6 is reachable, but we're saying we cannot be 6. And let me just note that one way of thinking about invariance is that if something is an invariant, it would be hard to find a counterexample to safety to that invariant. Let's assume we look at the picture and decide that we want to go ahead and prove some invariant about the state of that program given the picture that we draw. Sometimes a fact is so obvious that it's very hard to prove it formally. But here are 4 ways to show that this fact is an invariant. Well, the first one, it's obvious, duh. Second proof is that you draw a picture and you show pictorially that it's impossible for this not to be always the case. The other one is that we can write a sentence and argue about it in words, given mathematical or other facts. And then possibly the most precise way of thinking about this is to think about it by induction on paths. So the steps that are possible to take, not just the variables and values. So consider this property or any given property for any program. If we can take any arbitrary state and then by induction on a path that led to that state, show that that invariant is true for all given states, then by induction on that fact, we can reason whether that property always holds or not. And then in induction, we have a base case. So in our base case, we know that 5 is greater or equal to 5. That is true. And in the inductive case, we have to show that our transition up to step n was correct. And then from that, we can show that we can transition to n plus 1, and thus n plus 1 is greater than 5, and then our property holds. Now, this fourth example we gave is an inductive proof, but we are going to see that not all invariants are inductive, and we can reason about them by induction. But an inductive invariant has these properties. It holds in all initial states, and it holds when we transition from our base case to our inductive step, and then to our goal. And one important point for transition systems is that not all invariants in transition systems are necessarily inductive. And there are examples like this where there's an invariant that is obviously true, but if we want to use the inductive tool set, we'll get stuck and cannot prove them. So we have to resort to some other ways to prove those invariants. So let's think of an example where an invariant is not inductive, but it's still an invariant. Well, obviously, the base case should always hold because we always start from a base case. So even in our counter examples, our property holds in our initial states. So we're only left with this inductive case that can go wrong. Here, we can step from S1 to S2, but P may not hold in S2. And note that if S1 is reachable, that makes S2 technically also a counterexample to safety. But if we know that P is an invariant in that case, then S1 shouldn't have been reachable. So let's think of a possible state that can make things go wrong here. Now, let's consider this relation, which is, by the way, the same as this inductive state. In this inductive state, we are saying if these things hold, then this happens. Now, you can look up the truth table for an implication, but basically in an implication, we are saying in this state P holds. The only way an implication could go wrong or be false is that the hypothesis of that implication is true, yet the conclusion of that implication, the then, is false. So if we go fishing for states where our initial property, where our property holds at the beginning, but then we can step into a state where our invariant doesn't hold anymore, then we have found a counterexample to induction. This in and of itself is not reason to show what we thought as our property was is not an invariant. It just shows that we cannot prove it by induction. And here's another point to remember. if S2 is unreachable, and we have stepped into it in one step from S1, then that should mean that S1 is also unreachable. So if we find such a counterexample to induction, or such a S2 in a counterexample to induction, we can know that S1 should also be unreachable as well as S2. Okay, so let's consider this example here. We're gonna try to prove that n, or our state of our program, x, not equal to 4 is an invariant. Well, this is obvious. Our program initializes from 5, and then its state gets incremented. The third way of proving it also makes sense to us. But when we want to use our induction tool set, we run into trouble in the inductive case. So the base case, we can say that 5 and 4 are not equal, all good. But then here, in our inductive case, we run into trouble. Because we are saying that our program could be any natural number. And then given any natural number, we should take that natural number and be able to step into another state in our program, which is a valid state. Well, we said that 4 is not a possible state in our program, but we also allowed for natural numbers. Well, what are some other natural numbers? Well, we have 0, 1, 2, 3, and then in this case, in our inductive case, because we have allowed any natural number other than 4 to be our initial state in a transition, we can now say that stepping from 3 to the next number is possible, because we said that our transition works such that we can step from any natural number to another natural number. But then we are stepping into 4. Notice this kind of works with the hint from the previous slide or previous slides, where we said that if a state is not reachable, then most likely the state that led into it is not also reachable. So in this case, 4 is not reachable, but we stepped from 3 to it. So that means that probably 3 is not reachable either. But then what if we kept playing this game? And we see in these slides also that this is a counterexample to induction. Notice this is still not a counterexample to safety. But how do we fix this proof? This is rather a little bit funny. We have already proven that n is greater or equal to 5. Okay. So now we can just say that our knowledge that n is greater or equal to 5 implies that it's also not equal to 4. And that's it. We have bagged that fact. This technique is called strengthening. So again, to count the steps, we have to come up with an inductive invariance. And then using that inductive invariant, we can prove more facts about our program. So we just saw that sometimes proof by induction doesn't work. We need to strengthen. And then finally, here's a single slide takeaway for you. So when we are given a property P and asked to prove that it is actually an invariant, we want to take the following steps. First, we want to think whether it is really an invariant. Can we show in any of the previous ways, these other 3 easy ways that we showed before, that it is an invariant? And this also doubles as a search for a counterexample to safety. And usually it's easier to prove something by induction. So maybe we should try to prove this property that we think is an invariant by induction first. And then if we can find a counterexample to induction, we can work on strengthening this property into another property called Q, where Q is an inductive property. And then we can induct it.